All right, today we're going to take a look at yet another type of the test. And this is a new material, meaning that you probably did not see that material in Math 125. So what I'm saying is everything that we considered in this course so far was largely a review, hopefully, of the material that you knew already in one form or another from Math 125. So this material is the new stuff that is going to be on the exam tomorrow, obviously, and on the homework that I will assign today. Okay, and also here is the good news. All right, I guess if there are good news in this course. Every homework that I assigned so far are required from you pretty much to do the computations on your own, right? Confidence interval, for example, you have to find the mean, you have to find the t-value to use, you have to calculate the margin of error, and then calculate from that upper and lower confidence level. So there were some computations involved. The reason why I was doing that is I wanted you to see the underlying mechanics and principles of all these tests and techniques that we're learning, okay? This is going to be the last one of this type, okay? So chi-square goodness of fit test that we will study today is the last problem that we will do manually by hand in all the details, okay? The reason for that is we're kind of getting to the more or less complex methods and techniques. They are not very easily calculatable, okay? So the calculational difficulty of all these tests that we're going to study from that point and on is going to be prohibitive for us to actually look into the detailed formulas behind the scenes, okay? So all the tests, equations that we're going to study in the rest of this course, we have to use the software because otherwise it becomes computationally a very intensive problem, okay? And cannot be done easily. So, goodness of fit test for the chi-square distribution. All right, number one is this test is also called oftentimes Pearson's goodness of fit chi-square test, and it actually applies to the possible outcomes of multinomial experiment. So before we proceed with the test, we need to discuss what is a multinomial experiment. Well, you remember we studied binomial not so long ago, right? We said binomial distribution has the binomial experiment behind that. What does that mean? Experiment is some action that we repeat multiple times, right? So we set our mind, we say, let's say I'm going to do the same thing all over again 10 times, like flipping a coin, or going outside and asking a person on the street, I'm going to stop 20 people and ask them if they're left-handed or right-handed, okay? And the idea was that each time when you perform this experiment, a trial, like flip a coin or ask one person if they're right or left-handed, it can result in only two outcomes. That's why it's called binomial experiment. Only two possible outcomes, number one and number two, which you randomly call success or failure, right? And there is no judgment involved. We discussed that. You can call, getting a tails a success or getting head a success. It doesn't really matter. When you go outside, you can call a success person being left-handed or person being right-handed. Person voting for Democratic candidate or Republican candidate. No judgment involved. They're easily interchangeable. And also, the experiments or trials are independent from each other. So if you flip a coin, it doesn't matter what you got previous time, it will still be 50-50, right? If you're asking a person if they're left-handed or right-handed, it doesn't matter what happened with the previous respondent, it's still going to be like 10% versus 90, right? Something like that. So that's binomial. There are only two possible outcomes from each trial or experiment. Well, in general, it can be many outcomes, right? Nobody said that it has to be only two. It can be, in general, k, whatever number it may be, k, right? For example, so therefore, multinomial experiment is same idea, right? You perform n trials, but each trial, instead of two, as in binomial, can result in more than two. 1, 2, 3, 4, up to k. Can be any number, okay? That's why it's called multinomial and not binomial. For the example actually comes next. So one of the requirements is that probabilities for all these different independent outcomes have to adapt to 1, indicating certainty, right? So, for example, let's say here, how many cars can people, families, or households have? Well, some households don't have any cars, right? Especially in large cities, such as New York, probably, right? In New York, to have a car is very, very burdensome, right? So you have to pay for parking if you can find one. So you're better off just riding public transportation system. So maybe people that have no cars, right? At the same time, in places like Newport News that do not have a well-developed public transportation system, you have to rely on cars to some degree, right? So there are families with 1 vehicle, 2 vehicles, and then 3 or more. Let's put them all together. So if people have 3 cars, 4 cars, 5, whatever it is, right? We're just going to call them that. That's a lot of cars, category, multi-car category. So, and let's say that we performed analysis, okay, of people, took a sample, right? And it turns out that in our sample, can be fairly large, 13.5% of people have no cars. Okay, most people have only 1 car, 33.7. 2 vehicles, like husband and wife, they need to drive to different places, work, right? So 2 cars are required. About the same as 1 car, and only 19.3% of all families have 3 cars or more. Then these percentages can be treated or considered as probabilities, that you pick up a random person on the street, ask them how many cars you guys have in the family, and they give you one of these responses, right? So, coming back to the previous slide, if you add together different probabilities for different possible outcomes, they have to add to 1, telling you that we don't know which outcome will be observed in any random experimentation, but it certainly is going to be one of these possibilities, right? You either have no cars, or 1 or 2, or 3 or more. Okay? Now note that if k is equal to 2, if you have only 2 possibilities, you're back to our good old friend, binomial, right? Success and failure, only 2 possibilities. Okay? So multinomial, therefore, multinomial experiment is a general case of binomial, or alternatively, binomial is a special case of multinomial, right? Okay. Now that presents a problem actually. What kind of problem? When we had a binomial experiment, such as, for example, during the class we considered elections, right? There was an example, which candidate is going to win? We had a file with all the votes, right? If it's a Republican, it's a 1. If it's a Democrat, it's a 2. And then we tested the hypothesis, what is the likelihood, or we constructed the confidence interval also, can we claim that Republican is winning, right? And that was easy because, whatever proportion votes for one candidate, that's 1 minus proportion for another candidate, right? Because there are only 2 of them. So that was fairly straightforward. So therefore, we could pick one of the cases, success, failure, Republican, Democrat, whatever it is, male, female, right-handed, left-handed, pick just one of the options, right? And test the proportion for that specific option. And that's basically how we, I believe in the previous class, we looked at the example with State Farm Insurance, right? With the satisfaction survey, right? We did that. So State Farm Insurance says that the satisfaction level is more than 90%, right? So we're looking at proportion of satisfied customers, and we were testing this hypothesis, right? Alternative was that, no, you're too optimistic, and the actual percentage is less than 0.9. That was our research statement, right? While null would be 0.9 or more, that's consistent with what State Farm is saying, right? So one of these 3 forms we're testing only if we have 2 possible outcomes, or in other words, binomial experiment. Well, what if we have a multinomial experiment? How many proportions do we have? K, right? And therefore, you can't really formulate hypotheses in this form, just like we used to, okay? Because more than 2 proportions, that presents a problem, right? And we kind of have to test all proportions simultaneously. So therefore, we're going to have to figure out something more elaborate and more sophisticated than just testing one proportion. So let's take a look at the example, okay? Example comes from marketing. Two companies, A and B, recently conducted aggressive advertising to maintain and hopefully increase their market share. And these companies are in the business of making a fabric softener for laundry, right? So before the advertising campaign, company A was the largest player on the market. They controlled 45% of all the sales. Their closest competitor, company B, controlled 40% of the market. And as you can see, 40 plus 45, that's 85, right? Where is 15? Well, 15%, the rest of the market, was belonging split between smaller players, okay? So two major companies and a bunch of smaller ones. All right, now, let's say that we performed the advertising, companies A and B, right? They want to grab more market share. And after that, they would like to see how is the market distributed right now after we perform the advertising. So what do we do? Well, we have to ask people what their preference is, right? So what they do is they pick 200 respondents, 200 people randomly, and every person out of this 200 sample was asked, which fabric softener you prefer now? If the response was company A, we record that as 1. If the response was company B, we record that as 2. And if they said, I don't like A or B, I'm using something else, a smaller company, then we record that down as 3. So here is the punchline, right? Can we, after analyzing that sample of responses, conclude at 5% significance level that customer preferences have changed since before the advertising campaign? So see, the question, the way it's formulated right now, it's not really asking you, did company A gain the market share, right? Or did company B lose the market share? Or maybe A and B both gained because they advertised, right? And others collectively lost, right? It could be pretty much any kind of combination of these factors, right? How the market is distributed afterwards. So therefore, we can't really, we're not going to really test any specific proportion in isolation, but rather we're going to test them all together, okay? So let's go ahead and download the file. For that, we have to go to Scholar, right? As you guessed, undoubtedly. And after that, go to Datasets. Okay. Datasets for jump. And closer to the bottom, you will see the file that's called Fabric Softener. Let's open it up. All right, so here is my file. So you can see that I have 200 observations, number 1, right? And it's a mixture really, right? Company A, B, and then other every once in a while. So that's what we expect, right? The majority of responses is probably going to be company A or company B. But at the same time, every once in a while we have other, right? Okay, so now let's go ahead and formulate the hypothesis that we're going to test. All right? And you know what? I'm going to bring up notes. All right? So here is the hypothesis that we're going to test, null and alternative. Okay? Remember we discussed that. Null is status quo, right? Things, basically business as usual, right? Nothing out of the line. An alternative hypothesis would be a challenging statement, research assumption, right? What we're trying to test. So here is what we're going to test specific to that problem. Okay, my null hypothesis H sub 0 is going to be like this. After the advertising was conducted, after we ran the marketing campaign, the proportion of people who still like company, well, let me call it A. Let me erase that part. Proportion of people who still prefer company A is like what it used to be before the advertising. What is it, 45%? Yeah. So in other words, proportion of people who responded company A was 0.45. Proportion of people who responded I like still company B was business as usual, 40% as before. And proportion of people who said I still prefer smaller other companies is 0.15. Okay? In other words, I can state in plain English, Market distribution did not change, right? Company A still controls 45%, B 40%, and others still 15%. So market did not change. Market did not change. That's my null. Business as usual. Okay, status quo. Even after advertising, nothing really happened. Okay, so if my null says market did not change, what should my alternative say? It did change, right? Because alternative is reverse or opposite of null. Okay, so my alternative, I'm going to write it out actually in a couple of ways. Way number one is in plain English. Okay, so market distribution did change. Market distribution changed after marketing campaign. Well, changed is great, but in how many ways can the market change? Many different possibilities, right? For example, A can gain, B can lose, and others can stay the same, right? Or A can gain, B can stay the same, others can lose, right? Or both A and B can gain and others can lose, right? Or A can lose, B can gain, others stay. So there are a lot of possibilities, right? How do I write them out in one statement for my alternative hypothesis? Well, here is the generic form that statisticians agreed to do. I don't know how exactly market will move, but at least one of the proportions Pi, 1 to 3, proportion 1 or proportion 2 or proportion 3 has changed since it's pre-advertising level, right? Pre-advertising level. That would be yes, right? Level. Okay? And that covers a lot of different possibilities, but at least one proportion has moved. Well, obviously, if one moved, it's a zero-sum game, right? For company A to gain, somebody else has to lose. So therefore, at least one means actually at least two proportions, right? One moves up, another moves down, right? But that's pretty much how we're going to formulate that. Okay. Now, let's do the let's discuss. Okay. First things first, true or false? We start hypothesis testing by believing that the null is true. That's a general statement, right? We discussed it yesterday. Every time when you have hypothesis testing, we start by saying that let's suppose that the null statement is actually true, right? So I have 200 observations in my sample, right? N equals to 200 observations, okay? And I start by saying that null is true. At least that's what I believe in right now. If the null is true, I can calculate what should be the expected counts out of 200 people. How many people, if null is true, will still answer company A, will still answer company B, and will still answer company other, okay? And I'm going to call them expected frequencies, okay? E for company A, E stands for expected count. Okay, E for company B, and E for others. All right, so 200 people I surveyed, right? True or false? If null is true, then 45% of these 200 people should say they like company A. That is true, right? So 200 times 45%, that gives you 90, right? So if null is true, 90 of my data points should read these people like company A. I'm going to do similar stuff for company B and company other. So if null is true, then 200 people I surveyed and 40% of them should still like company B, correct? So therefore I multiply that by 0.40, and what's that? What's 40% of 200? 80, right? 80 people should say company B, and other, that's 200 people multiplied by 15%, and that should give me 30 people, right? This is what I should see in my sample if null is true and market did not change even after advertising, okay? Now, what I have is probably different. Okay, so let's go back to jump and let's see what are the actual frequencies. I'm going to call them actual frequency of response A, actual frequency of response B, and actual frequency for the response other. Okay, so all I have to do really is to analyze my sample, right, and find out what are the actual counts. All right. So I'm going to switch to jump, and very easy, right? I have to look up the distribution of this data sample. So go to the distribution, select softener, and move it to columns, and then click OK. There you go. So I can place it horizontally. My counts are really right here, right? It lists all the possibilities, A, B, other, and the counts are 102 for A, 82 for company B, and 16 for the other. So I'm going to go back to my notes and just say 102, 102, 82, and the last one was 16? 16, okay, good, 16. All right. So I see some differences, right? It's not quite the same as what my null would say, okay? So if null was true, then I would expect 90 people to say company A. In actuality, it was a little bit more than that, 102. 80 people would say company B, and I saw 82, which is fairly close, right? And 30 people should say company, well, other companies, and only 16. Now, big question is that close or is it far? So obviously, what would happen, suppose, for example, suppose that these numbers would be exactly 90, exactly 80, and exactly 30. What would I say? Which one of these hypotheses is true, null or alternative? Null, right? Because what I see in the sample exactly corresponds to the null, right? In what case would I start more and more moving towards the alternative? If I see big deviation between what it should be and what it is, right? So right now, it should be 90 if null is true, but it's actually 102. So there is some difference, right? Right here is another source of difference. That difference for company B is not that high, right? But of course, the question is, again, what's a big difference and what is not so big difference, right? Now, for that, ladies and gentlemen, I have to compute a weird thing, okay? Let me go back to the slides and show you the formula, okay? All right, here is the formula, okay? I have to take my actual frequency from the file, subtract the expected frequency, if the null is true, assuming that the null is true, square that distance and divide by E, and then add together across all the categories, okay? Well, let's do this, all right? So, and that awkward value is going to be called chi-square, okay? Chi is a Greek letter, and it looks a lot like English X, but it's a little bit fancier, okay? So this is how you write it down, chi-squared. So I'm going to compute a chi-squared statistic, okay? So again, it's the sum for frequency of the response minus the expected frequency if the null is true, squared divided by the expected frequency. And I have to take sum for all categories from 1 to k. How many categories do I have in my specific case? 3, right? I have 3 responses, A, B, and other. That's what I'm going to do. All right. Well, let's do it, right? So the first one, oh God, I forgot. What was the first frequency? 102, right? 102, and I was expecting 90, right? Minus 90 squared divided by 90 plus. The second one is the actual frequency was 82, I believe, and I was expecting 80, square that, and divided by 80. And the third one, the actual frequency was, oh God, 16, right? 16, 1, 6. And I was expecting 30, square that, divided by 30, okay? And let's find out what that is numerically. Well, we're going to use a big fat calculator, otherwise known to humanity as Excel, right? All right. So let's switch over to Excel. I'm going to start Excel. So very simple computations, right? So the first thing is going to be 102 minus 90. That would be squared divided by 90. That's the first term of my sum, right? The second term is I observed 82 minus 80 squared divided by 80. And the third term is I saw 16 while the expected is 30. That would be squared and divided by 30. Okay. And I have to add them together, right? So my chi-squared, and this is, by the way, it's pronounced chi-squared, but it's spelled chi-squared. Chi-square. Not even squared, chi-square. That's how the distribution is called. Don't know why, quite honestly, because it's supposed to be chi-squared, but typically statisticians say chi-square. Right? So all I have to do is take the sum of these terms. And what I have is 8.1833. Okay? So let me go back to my notes. 8.183333. Right? Now, ladies and gentlemen, true or false? If my chi-squared value would be 0, my null, I would pick null. Let me explain where I'm coming from. In what case my chi-squared would be exactly 0?
If there was no difference at all.
If there was no difference between the expected frequencies and the observed frequencies, right? And what are the expected frequencies? What I expect to see if the null is true, right? So therefore, if there is no difference between my expected numbers and observed numbers, and I'd say, well, that matches precisely what the null hypothesis would give me. So therefore, I pick null, right? So if chi-squared, I'm going to write that out, okay? If chi-squared value is equal to 0, then we have overwhelming, strong evidence to support the null hypothesis, right? So I'm going to erase that ugly arrow and replace it with a nice and cute one. All right, so therefore I pick null hypothesis is supported, right? Supported, okay. Now, true or false, as I start seeing larger and larger differences between what's expected and what's observed, that's when my chi-squared goes up. This computed value. So the larger the difference between f and e I see, the larger the whole expression becomes, right? So therefore I'm going to say as chi-squared goes up, I have more and more I have less and less support for the null hypothesis, and therefore more and more support for the alternative, right? As I'm getting away from the null, I'm kind of moving towards the alternative, right? So as chi-squared goes up, more, so H1 is supported more, right? Supported more. So at some point, when my chi-squared becomes sufficiently large, it's kind of like there should be a switch, right? Like we flip a switch and we say, well, no, we deviated far enough from what's expected if my null is true, so therefore now we believe the alternative, okay? But of course the question is, where is that thing, right? Where is this magical value? Once you cross this threshold, all of a sudden you don't believe in null anymore and you support the alternative. Well, let me give you a graphical picture, okay? So here is how chi-squared distribution looks like. In general, chi-squared distribution, it does not go below 0, okay? So this is chi-squared. 0 is the minimum, and it's very severely skewed to the right. So here is the typical picture how chi-squared looks like. You have a peak, whoops, that's kind of ugly. You have a peak, and then after that, starts to go downhill. And it doesn't have this peak right here. It just keeps going, keeps approaching horizontal line, okay? So, as we were saying, if my chi-squared is right here in the null, at 0, right, then what hypothesis do I pick, null or alternative?
No.
Null, right? If chi-squared is precisely 0, that's my null right there, okay? If I start increasing chi-squared, make it higher and higher and higher and higher, I'm kind of deviating from the null, right? So high values of chi-squared tell me that that alternative might be true, right? Low values tell me that the null might be true. So this is what I computed specifically, right? Oh my god, it's so hard to draw when you're holding pen vertically. So specifically in my sample, I computed the chi-squared equal to 8.18 or whatever it was, 1833, right? 3333, okay. So my p-value, remember, what's the interpretation of the p-value? It's the probability to see what you see, or even more extreme if the null is true, right? If the null is true, I must be right here at 0, right? But this is what I see. Where do you think graphically I have points which are even more extreme? Everything to the right. So therefore, when you're testing chi-squared distribution, your p-value is going to be in the right tail of the chi-squared distribution, because that's where even more extreme values are located. So here is your p-value. Okay? So essentially, what I need to do now, ladies and gentlemen, is to find the area in the right tail of the chi-squared distribution, and I'm good to go. After that, it's business as usual. Here's your p-value, here's your significance level. Do you keep the null or do you reject the null, right? The only thing that I still have to mention is chi-squared has only one parameter, okay? So how do we find the parameter? Parameter, just like in t-distribution, is called degrees of freedom, df, okay? And it's very easy to compute. Remember what was the degrees of freedom for the t-distribution? N minus 1, right? Sample size -1. Here is the difference, okay? In the chi-squared distribution, the degrees of freedom is equal to k minus 1, not n, where k is number of categories. Number of categories. So in our case, how many categories do we have? 3, right? Company A, company B, and others. So therefore, in my case, k minus 1 is going to be 2. So I have to look in the right tail of the chi-square distribution with 2 degrees of freedom. Everything to the right from 8.18333. And that'll give me the p-value. Okay? And after that, I will be able to judge, am I far enough from 0 to claim that the market changed, or am I not far enough from 0? So at that point, we have to engage the software, right? So let's go back to jump. So as you probably kind of figured by now, I'm showing you the long and painful way, right, to do this problem. And that's what I will ask you to do actually on your homework as well, right? But again, like I said, this is going to be the last problem where we have to suffer through the pain of manual or semi-manual computations. Because we reach the borders of the civilized world in statistics, right? Anything beyond that is driven by software, because we cannot do anything manually after that. I tried before, didn't work. So we shouldn't even try. Okay, so let's go to the distribution calculator, right? Because all of the distributions are located there. Remember how to get there? You go to Help, Sample Data. Okay, and we go to Teaching Scripts, Interactive Teaching Modules, and Distribution Calculator. And there it is. And that tool should be smart enough to tell us about the chi-square, right? So I have to pick the chi-square from the list. And there it is. Chi-squared. Degrees of freedom? 2. And it has actually another thing, non-centrality. So there are 2 types of chi-square distributions, central and non-central. We're going to use non-central, okay? So non-centrality should be 0. All right, what we're looking for, input values and find probabilities, or input probabilities and find the value. We're looking for p-value, right? P stands for probability or proportion, right? So therefore, we have a value, and we need to compute the corresponding probability. Okay, and that would be in the right tail. We just discussed it, right? So x greater than q. That would be the right tail. And what's my value? 8.1833. That's it. And when I hit enter, there it is. Okay? Probability in the right tail, you can see that right tail is very small, right? And the probability is small, 0.0167. I'm going to write that down. So p-value right there is 0.0167. Oops. 67. Okay? All right. So now we have to conclude our hypothesis and formulate the findings, right? What do I do with this p-value? What do I compare it against? Oops. Yep, significance level, right?
So there's another way that you can get there.
Oh yeah, absolutely. I'll show you a quick way to get there in just one sec. So I want us to suffer through the pain of calculations, and then I'll show you that it takes literally 2 clicks to get there, if you know how to use jump, right? So obviously it's less than 5% standard level of alpha, right? So what do we do between our null and alternative?
It's low.
Reject the null, right? Yep, reject the null in favor of alternative, and let's go back to the null and alternative. Okay, right there. So low p-value, I reject the null in favor of alternative. What does my alternative say? At least one market share has changed as the result of advertising, right? So it basically says that the market was redistributed, right? Now note that this test is kind of non-specific, right? It talks about market in general, but nothing particularly, right? It doesn't say that company A gained the market share at the expense of others, right? Or company A gained, company B lost, and others stayed the same. Nothing like that, right? It basically says, is the market still the same, or is it somehow different? And our finding says it's somehow different, right? It does not. It's kind of like the good analogy that I like to use is it's the smoke detector. When smoke detector goes off in the house, you know that there is a smoke, right? So somewhere there should be a fire. Does it tell you where the fire is? No, somewhere, right? Same thing here. Market changed, so smoke detector goes off, right? How did the market change? That test doesn't tell you. Okay, so it's more high-level test. Okay, it does not test specifically A, B, or others. It tests the distribution in general. Make sense? All right, well, the last thing to do is to see how easy that would be in jump, right? So remember that number, 0.0167. That's our p value for the hypothesis test, right? So now, if I go back to my original data, here's my original data, and I believe I did actually, well, let's do it again. I'll look at the distribution of softener, and there it is. I did that before. So here's how the nominal, this is nominal data, agree? Categorical nominal data. All right, and all I have to do really is to go into the red triangle menu. As you guessed, everything is in the red triangle menu, right? And over here, test probabilities. And right there it says, well, your estimated probabilities as they are in the sample are 51% for company A, 41% for company B, and 8% for others. What are we testing? Hypothesized probabilities. So I should enter over here the probabilities that I have from my null, right? So company A still controls 45% of the market. Company B still controls 40% of the market. And others collectively still control 15% of the market. Okay? And then I click the done button. It says, well, here is the results. Remember I told you at the beginning that this goodness of fit test sometimes is also called Pearson goodness of fit chi-squared test, right? Do you see the Pearson line? And probability greater than chi-squared, that's your right tail of the chi-squared distribution, right? As we just discussed. Is that the same or is it different? 0.0167. That is the same, right? But now you know how this number comes to the existence, right? So you saw all the mechanics behind that. So that's a long way to do this problem and a short way to do this problem, right? So your homework contains one problem which is very similar, and you will be asked to do exactly that and find the p-value and chi-squared and the right tail of the chi-squared distribution, p-value, and conclude the test, okay? But that's the first and the last time when I will ask you to do that. From that moment on, I'm going to assume that you're familiar with this thing, you understand the basic principles behind this test, and using the software as the shortcut to eliminate manual computations, that would be a right thing to do.
This is much more intuitive than these are two.
Yeah.
Much more intuitive.
Yep, I agree.
Are we always going to leave it where it has the first option already selected and not pick the second one?
The first.
For the test probabilities.
Oh yeah. Huh?
The omitted thing.
Mm-hmm.
Let
Yeah, just leave it as is, and then proceed. Okay. All right. So let's take a 10-minute break, and then when we come back, we'll take a look at comparing two populations. Okay, now let's switch gears a little bit. Again, this is material that you didn't probably cover in Math 125, so this is new for you, I'm suspecting. And let's actually start using our analysis flowchart. This flowchart you can download from Scholar website. Okay, I told you at the beginning of the class that this flowchart essentially shows the structure of the course, right? That's pretty much all that we're going to learn as the result of this class, hopefully. How to use different tests, and what the tests are, and what kind of data do they test. So everything that we did so far was kind of revolving around one single population, right? So as you can see, I'm going to zoom in. As you can see from this chart, statistics, as we're going to study it, has 4 different parts, right? One of them is describe a single population. Another part is compare 2 populations. Another part is right here, compare 3 or more populations simultaneously together. And finally, this one is kind of important, very popular topic, analyze relationships between 2 variables, or between 3 or more variables. Okay? So far, everything that we did was actually right here. Describe a single population. And also, if you look at different trees, decision trees in this flowchart, you can see that the first question, after you know what type of problem you're dealing with, like are you describing one population or comparing 2 or 3 or a relationship, the first question is what data type are you dealing with? What data type are you dealing with, right? So here's what we did so far. Based on the data type, you're going to end up with different techniques and methods, right? So for example, if you're looking at the interval data, meaning it's numerical or continuous, right? What type of descriptive measurement are you looking at? It can be a measure of central location or variability. Well, we didn't really talk about how do you assess variability. There are tests to do that, okay? Tests primarily about sigma squared. That would be variance of the population. So our efforts were concentrated on central location, and that would be mean, right? So what did we do? What did we do for the mean? Well, we did a couple of things. Number one is confidence interval. That would be estimation of the mean, right? We're saying mean is somewhere between lower and upper confidence level, and we're 99%, 95% certain, confident in the answer, right? So that would be estimation of the mean, or testing of the hypothesis, okay? That would be t-test. That's pretty much what we finished a couple of classes ago, okay? If you are dealing with nominal data, then there are 2 possibilities. Number of categories, right? If you have 2 categories, then you're dealing with binomial experiment. Remember we discussed binomial distribution, and the only thing that you can do, well, what you can do with it is estimate the proportion using the confidence interval again, okay, or test for the proportion. Like the example would be a couple of classes ago we looked at State Farm insurance, right? Is that true that their percentage of satisfied customers is less than 90.9, right? So therefore, we're using the hypothesis testing, and it's not a t-test as it is for the numerical data, but it's a z-test, right? So when you have binomial experiment and there are only 2 possible outcomes, success or a failure, you can estimate the proportion using CI, confidence interval, or you can test the hypothesis. What happens if your nominal data has more than 2 categories, 3 or more? Well, we just finished that part, right? We had a sample of 200 people, and every person was saying they like either software from company A or B or others, right? And in that case, you're using chi-squared goodness of fit. That's what we just finished. So therefore, largely, with the exception of the variability, we didn't touch variability at all, right? We covered these 3 things, right? T-test and confidence interval for the mean, Z-test and the confidence interval for proportion, and also chi-squared goodness of fit. So we're pretty much done with this first decision tree, okay? So second decision tree is going to be compare 2 populations, right? And as you can see, the first question is exactly the same. What data type are you dealing with? Is it nominal, ordinal, or interval? So we're going to start today with interval, okay? And again, variability we're going to leave, outside. We're not going to talk about how do you estimate the sigma. Same thing can be done. You can estimate sigma in terms of confidence interval, and you can test hypothesis for the sigma as well, okay? But we're not going to even try that. So variability is not part of this course, but we will concentrate our efforts on central location. And you can see the next question, important question that you have to ask is, what are you dealing with? Is it independent samples or matched pairs? So today we're going to start looking at what is the case with independent samples and what's matched pairs, how to differentiate between them, and how the analysis differs, okay, in this case. All right, so we will talk about inference about comparing 2 samples of data, 2 populations. Okay, cool. So in the previous lectures, when we discussed confidence interval and the mean, and the hypothesis testing, right? It was about one single mean and one single proportion, depending on what data type you had. Was it numbers, or was your data non-numerical, categorical, okay? But every time we talk about only one single measurement. It's either mu or pi, okay? Now that we are considering a more complex case, when you're comparing 2 samples of the data, 2 means should be involved and 2 proportions should be involved, right? Mu1 and mu2 for sample number 1 and for sample number 2. Well, here is the preview of what we're about to do. Everything that we will do, all tests, will be about not the mean of the sample 1 and then also mean of the sample 2. Everything will be, that we will test is going to be about the difference. Mu1 minus mu2, mean for the population 1 minus the mean for the population 2, or same thing about proportions. Proportion 1 minus proportion 2, okay? And our assumption, of course, is that we don't know anything about the population, right? And that's actually realistic because, let's say, good example would be advertising, okay, from marketing. How is that relevant, what we're doing, comparing 2 populations to the business, right? What kind of business examples can we have? Why companies do marketing, advertising? What's the purpose? What's the goal? What are they trying to achieve?
More money.
More money, more sales, right? They're trying to generate more sales, bring more customers. So therefore, it only makes sense to expect that sales before the advertising are going to be lower than sales after the advertising, right? Well, it sounds very good theoretically, but is that really happening? How do we measure? Well, one of the ideas would be, how about I pick a store or a number of stores, right, and measure sales in these stores before I advertise. However I decide to do that, okay? I may just go ahead and measure, for example, total sales, okay? Total amount of money that the store is generating every day. If I'm looking at sales overall, right? It's like Walmart, for example, when they put a commercial on the TV, commercial can be specific to the product, or it can be just general, right? Specific to the product can be, hey, we have a lawnmower for $99. It's a special, go buy lawnmowers, right? So they can expect the sales of the lawnmowers to go up, but not anything else. Maybe, but hardly, okay? Or it can be just general commercial, right? Promotion materials that says Walmart, always low prices. Okay, what do they advertise? Nothing specifically. They just say, hey, our prices are low, come shop with us. After that, they probably can expect sales to go higher broadly, right, across all the categories. Okay, so how can I ensure that sales? How do I test if sales go up after I advertise? Well, pick number of stores, record how much money they generate on a daily basis for several days, right? And then after that, run the advertising and do the same measurement and see if the sales in general go up. Is it possible that in some stores sales, contrary to the expectation, will go down? Just for whatever reason. Possible, right? Why? Because what happens when it rains? People don't go to the stores all that much, right? So I can advertise, but if it's a rainy weather, less people go out. So in spite of my best efforts, sales did not go up. That can happen, right? So from the pre-sales to the post-sales, it's not necessarily that all sales will go up universally across the board, right? I will have probably mixed results, but in general, the tendency should be they go up, okay? So the only thing that we know when we're picking up our sample is what's inside the sample. That's the only information that you have, right? We don't know anything about the means, about standard deviations, how things are distributed normally, non-normally. Nothing is known, right? So we're going to assume general case. All right. So here is basically how we're going to perform this test, okay? That somehow it got cut. I don't know why. All right. What I'm trying to test is the difference between the actual population mean 1 minus the actual population mean 2, right? Problem is, I don't know mu1 or mu2, right? And I never will. We discussed that. Population data, more frequently than not, is not accessible for statisticians, right, for analysis. So therefore, what do? I pick a sample, right? So sample from population 1, sample 1, is going to be my first piece of evidence, so to speak, and sample from the population 2, the second piece of evidence. And guess what? They don't even have to be the same size, right? So number of items that I pick for sample 1 and 1 may be different from N2, from the sample number 2. So remember when we discussed the flow chart, right? When it comes to comparing two populations for the numerical data, eventually you bump into the question how data are collected. It's called experimental design. Are you dealing with independent samples or matched pairs? Let's discuss what is the difference. Here's the difference. Independent samples, first of all, they do not have to be the same size. Again, it got cut. I don't know how that happened. So size N1 can be different from size N2, but most importantly, it's not the main thing. I mean, even if it's the same size, that does not mean anything about, is it matched pairs or independent samples? We don't know. It's all in how the data are really collected. So I'm dealing with independent samples if samples are collected independently. What does that mean? I close my eyes. Okay, well, no, not yet. Okay, I pick sample number 1 randomly. Purely randomly, okay? So when I get my sample 1, now I close my eyes, I forget about the existence of sample number 1, and I blindly, also randomly, pick sample number 2. So coming back to our sales example, in case of Walmart, right, running their advertising campaign, here is how random samples can be collected. I want to run the marketing ad on the internet or on the television, whatever it is, right? And I randomly pick number of stores. Okay, how many stores Walmart has, estimatedly, in the U.S.?
Thousands.
Several thousand, probably 3,500 probably stores or something like that. So I randomly pick, let's say, 500 stores. Okay, so I have a list of 3,500 stores. I generate 500 random numbers between 0 and 3,500. Bam, that's my sample. Okay. I set it aside while I measure all the sales, of course, in these stores, right, before I do the marketing. Then I run the advertising, and I do, again, random selection, as if nothing happened before, okay? Has no connection, my second sample, has no connection with sample 1. Some stores that I pick for sample 1 can be the same, some stores that I pick for the sample 2 can be the same as in the sample number 1, right? purely accidentally, randomly. Most of them probably are going to be different, right? But I forget, I close my eyes, and I behave as if nothing happened. There is no sample 1, okay? So sample 2 is freshly selected, completely random, has no connection with sample number 1, okay? Completely independent choice of items, okay? That would be independently collected samples. But you can say, well, is that really fair to make this comparison? Here's what can happen, okay? True or false? Walmart, different stores from Walmart can be different in terms of the size, right? Like for example, the smallest Walmart store that I saw was in Atlanta, Georgia. There is a pretty good university there called Georgia Tech. You probably heard about that one, right? It's a pretty good engineering school. And it's located not in the downtown Atlanta, but within the city limits. And right there, on campus, like one of the academic buildings, the first floor of the academic building is actually a Walmart store, okay? Very small. I mean, it's not small, it's not like your 7-Eleven size. It's more like a regular grocery store, but it's not gigantic supermarket as you're used to, okay? So that would be a small store for Walmart, right? Very small. So can it be the case that accidentally, like I had no small stores in my sample number 1, and purely randomly, in sample number 2, I got some small stores. Just because of choice, right? Randomness of choice. Can be the case, right? In this case, that would skew the results a little, that would change the results a little bit, right? Because it's not fair to compare a regular supermarket, with a smaller store, right? Sales will be smaller, not because of advertising or not just because of pure size of this thing, right? Also, one store can be located kind of in the middle of nowhere, right? And Walmart sometimes builds stores this way, right? So, for example, there are 3 small places, 3 small towns, and every town is fairly small, so it's not enough customers to build a store in there. So they build a store in the middle so that it will serve the surrounding community, right? So if the store is located in a low populated area, sales can be low in general, right? As opposed to in the middle of Newport News, right? People come to shop from Newport News, probably some from Hampton, right? From Williamsburg, from Yorktown, all over the place, right? So there are a lot of factors, okay, that can play into the comparison of 2 independent samples. How do I isolate these factors and kind of drive them away? Well, one way to do it is to have more controlled choice of stores, okay? So what does that mean? Really, the only random sample that I have is sample number 1, okay? So before I advertise, before I run the marketing campaign, I'm going to say, well, let's generate 500 random numbers between 0 and 3,500, and that would be all stores that I pick in the US, okay? Then I run the advertising, and how do I make the comparison fair? I pick not just random sample number 2, but I pick same exact stores, right? So therefore, there is no such thing as difference in demographics, or in population density, or store size. It's all identical for before campaign and after the campaign, right? So I'm going to eliminate all these random effects that I would have if samples were independently picked. Okay, so now I'm comparing same store to itself before advertising and after the advertising. And that probably will give me a more purified effect, right? I'm not going to look at anything else but the effect of advertising on the sales, right? Because it's the same location. So in other words, my sample number 2 is hand-picked, okay? Sample number 1 is random, and after that I hand-pick observations in the sample number 2 and match them somehow. So store example is just one case, right? How you can match observations. It's the same store, right? Therefore, observations are really matching. It can be something else, okay? For example, I'm not going to reveal any secrets. I'll assign homework, and then you will see if you can spot, what are we dealing with? Independently collected samples or somehow matched observations, matched pairs, okay? All right, now, I don't know if I want to. We're going to talk a little bit about how hypotheses are being formulated, and then we're going to take a look at the problem. Okay, just to give it a practical spin. So remember 4 different ways how we create hypotheses, how we test the hypothesis. We just discussed them, right? So way number 1 was null is that the mean equal to 0, for example, right, or a number, equal to a number. And alternative would be mean is not equal to a number. Okay, that's for number 1. And then another form is null mean is greater than or equal to a number, and alternative is mean is less than a number. And third form is opposite, right? Null is mean less than or equal to a number, and alternative is mean greater than a number. Okay, so that's what we did so far, right? When we discussed one single sample. So now that we are comparing 2 populations, remember several minutes ago we discussed that we're not going to test mu1 or mu2 separately in isolation. We're going to test a combination, specifically difference, right? Same 3 forms, form 1, form 2, and form 3. But instead of one mean, mu, now we have a difference, mu1 minus mu2. That's what we're going to test, okay? When we're comparing 2 populations of numerical data, we're testing not mu1 separately from mu2, not individually, but one minus another. And all of our conclusions are about one minus the other, okay? All right. Now, this part I want to skip because it has a lot of formulas which are not really, we're not going to use them, okay? I told you that we crossed into the unknown territory, right? Nothing that we do in these problems can be done, I mean, it can be done manually. It's just tedious and boring and not educational, okay? So I'm not going to bore you with formulas behind all of these tests. So therefore, let's go ahead and analyze specific problem. One important thing to remember, actually, let me go back one slide, okay? One important thing to remember is I can use t-test for testing difference between 2 samples only if my sample 1 is normally distributed and sample 2 is normally distributed. And you can actually see that in the flow chart. So let's go back to the flow chart. Look at that. If I'm dealing with 2 populations, data type is numerical, interval. We discussed that variability we're going to leave alone, right? Not even get there. So I'm obviously looking at the central location. If I'm talking about independent samples, population distributions. If it's normal, if both samples are normally distributed, then I can use my good old friend t-test to test the hypothesis that I formulate. But if one of the samples or both of them non-normal, then t-test cannot be used and I have to use something else, okay? And that something else is called non-parametric statistics. We're going to discuss non-parametrics at the end of this semester, okay? So, important point here to remember is when I'm dealing with independent samples, I have to test separately sample number 1 and sample number 2. If both of them pass the normality test, then I can use the t-test. If one of them turns out to be non-normal or both, then that's a red flag. T-test is not valid anymore, okay? All right, so let's take a look at this specific problem. It has to do with vendor selection. Okay? Vendor selection is an important issue in operations management, supply chain management. How do you pick vendors at shipyard? Is there vendors?
Oh, there's a crap load of vendors.
But there is a vendor certification program of some sort, right?
They're on the qualifying vendor list.
Yep. So if, for example, a new company wants to become a vendor, supplier for the shipyard,
We will send a bunch of folks out there to audit the company, look at their books and records, and look at their production facilities.
okay. So there is a
Qualify them.
qualify them. Okay. So there is a certification process, right? A lot of companies work this way, actually. Like, for example, if I'm, producing and selling electronic components, I can become Dell supplier. Dell has formal procedure. You apply they probably audit you, right? They look at what you're doing, how you're doing that, and then you become supplier. So,
Since I was a boss, I always picked Hawaiian trips.
oh yeah, of course. Yeah, it's far away, so I'll take the bullet, right?
I'll take the burden off of you.
Makes sense. It's about picking the Olympic team supplier. Okay, the Thorndike Sports Equipment has submitted a bid to the U.S. Olympics Committee to be the selected supplier of swimming goggles for the U.S. swim team. Currently, present supplier for the goggles is called OptiView, and they've been supplying goggles for many, many, many years. So Olympic Committee says, why would I choose a new supplier over the old one? Well, the only reason is if your product is better, right? And what's better? Well, what's primary thing for goggles? If you ever use swimming goggles, you know that when it starts leaking, right, then your vision is blurry and really it's useless, right? So therefore, Olympic Committee says, here, we're going to perform a standard leakage test. How is that done? Well, they pick a dummy that simulates the human face, right, and place goggles on the dummy. And then they start drown the dummy, submerge into the water. And at some depth inside, down in the water, it starts leaking the water and therefore basically stops working, right? So the larger the depth, the leaking depth, the better the goggles, right? The better the quality. So they're going to say, well, we're going to pick 50 goggles from our current supplier, OptiView, put them on the dummy, drown the dummy, and see when it starts leaking the water, okay? In terms of meters. And then we're going to pick 50 goggles from you, new guy, okay, Thorndike. And do the same thing, okay, place goggles on dummies, drown the dummies, and see at what depth we have water trickling in. And then after that we have to estimate which goggles are better, yours or the current supplier. And if yours come up on the top of the competition, then we have no problem, we'll pick you as the supplier. If not, sorry, we have a supplier already, your goggles are not good, why would we switch, right? Okay, so let's take a look at the data. Okay, sorry. Whoa. Goes in circles, right? Okay, I uploaded the data yesterday, I believe, on Scholar. The data is called Thorndike. Why is it SAV?
Because it looks like it's SPSS.
Yeah. Oh, God. All right. Hold on. I'm going to... I didn't realize that it's still old. Yeah. I'm going to change the data. All right? Give me a sec. Okay, now that I uploaded the new file out there, let's download the file, Thorndike Jump, and open it up. Double click, and there it is. Okay? So, like I said, I have two columns of data, right? Each column contains 50 items, right? 50 goggles from the manufacturer Thorndike and 50 goggles from the manufacturer OptiView. Now, the question is, do I have independently collected samples or do I have matched pairs? Here is basically what matched pairs means. If I have matched pairs, that means that my observation number 1 from Thorndike and observation number 1 from the OptiView, they will have something in common. Remember we discussed the sales in the store, right? It has to be the same store, right? If that would be sales, it has to be the same store. Same thing about line number 2, okay? Observation number 2 in Thorndike should have something to do with observation number 2 in the OptiView. So it's the same store, but different from the first line, right? And then third line, it's the same store, but different from the line number 1 and line number 2. What do you think? Can we link somehow these two goggles, number 1 and number 1, or are they completely random and independent? Is there anything that links observations that are on the same line? Or samples were collected independently from one another? Independently means we just pick randomly 50 goggles from one, measure how long does it take for them to start leaking, and pick 50 random goggles from the supplier number 2 and do the same thing. Isn't that how the experiment was performed? Pretty much, right? We picked 50 random goggles from first manufacturer and picked 50 random goggles from the second manufacturer, right? So these two goggles on first line, nothing links them, right? They were randomly picked from different manufacturers. So therefore, we're dealing with independently collected samples, right? Okay. Now, here is the kind of bad news for us, okay? In order to perform the analysis, the comparison test of the mu1 and mu2, JUMP actually requires something that's called stacked column, okay? But before we get into that, let's check the required condition. Can we even do any type of testing? What do we need to test? Normal. Sample number 1 is normal and sample number 2 is normal, right? Remember, when things are independently collected samples, you have to test each sample individually, okay? So let's do that. How do I do that? Very simple. Let's plot the histogram for both of them, right? So I go to the distribution and say Thorndike and OptiView. How do I select them both and plot them, right? And let me go ahead and stack them. All right. So what do you think? Sample number 1, Thorndike. Does it look more or less normal to you? It does, right? How about sample number 2, OptiView? It's a little bit skewed. In what direction? To the right. But overall, it doesn't look too terrible, right? So by the visual inspection, I'd say we're okay. Now let's take a look at the normal quantile plot for both of them. Thorndike, normal quantile plot, and points are supposed to align along the diagonal, right? Do they? They do pretty well. So first sample is normal, and let me do the same thing for the OptiView. OptiView normal quantile plot. What do you think? PDN, right? Pretty darn normal. And finally, let's go ahead and fit the normal curve into each one of them and use Shapiro-Wilk test. So sample number 1, I'm going to say continuous fit normal curve. And here it is, normal fit. And in the normal fit, I'm going to ask for goodness of fit, how well my normal curve fits the distribution, right? 0.6355. That's a high p-value, right? Therefore, what do I conclude? Between the null data are normal and alternative data are not normal, I pick the null, right? Null stays, I don't reject it. And actually, there is a confirmation from me. Note, data is from the normal distribution. So sample 1, Thorndike, is looking good. Now let's do the same thing with sample number 2. Again, I'm going to fit normal distribution, fit continuous fit normal. And it's right there. And here I'm going to ask for goodness of fit. And it says p-value for the Shapiro-Wilk test is 0.36. Again, high p-value, right? Again, I keep the null. The data are normally distributed. And it says data is coming from the normal distribution. So check, check, right? Both samples are normal, so therefore I can go ahead and use the test. But before we go ahead and use the test, let's actually formulate what exactly we're testing, right? Before even getting there. Okay, first of all, true or false? I'm testing to see if the new supplier is better, right? That's the purpose of the test, okay? And that becomes what? My alternative for the null. The new supplier is better. No? If I believe... Alternative, right? That's the research thing, right? That's the research statement. Whatever you're trying to investigate, you place that in your alternative hypothesis, right? So therefore, here it is, okay? I'm going to write it out in, oops, not null, alternative. I'm going to write it out in plain English, right? I'm going to say Thorndike is better. Thorndike is better. Okay. All right. What does that mean? Thorndike is better. Well, in terms of goggles, right? We're not evaluating them on the quality of their moral character, right? We're evaluating them on the quality of how well their goggles hold the water, right? So, if Thorndike is better, the average leaking depth for the Thorndike is going to be higher or lower than for the OptiView. How does that compare to the current suppliers, OptiView? Lower?
Lower leakage, right? A lower amount of leakage.
Well, what we measure is how deep you submerge the dummy before it starts leaking. High, right? So the higher the depth, the better the goggles, right? They hold the water until greater depths, right? So therefore they're of higher quality. So therefore the average leaking depth is going to be higher for the Thorndike than it is for the OptiView, okay? And by the way, just as we're on the subject actually, let's take a look, okay? It's not clear cut. If you look at these things, like for example, the first one, or maybe it is clear cut actually, right? The first one, 109 versus 77. So Thorndike holds the water better, right? 96 versus 87. Well, here is the reverse thing, right? Thorndike started to leak at 93 meters, while OptiView was holding up until 102, right? So it's not like all the goggles, they hold the same, they hold the water equally nice, right? So sometimes Thorndike is better, sometimes OptiView is better. But we're talking about averages, right? Okay, just wanted to make this comment. So this is my alternative, right? That the Thorndike average leaking distance is higher. But remember, everything that we do is about mu1 minus mu2, correct? So therefore, I have to take my alternative hypothesis in the form that it's presently in and convert that into this form, right? Mu1 minus mu2. How do I do that? Well, the easiest way to do that is subtract the same thing from both sides, right? What is that from the both sides? I have to subtract mu for the OptiView from the right side and subtract the mu from OptiView from the left side. And therefore, after that, my alternative will take the following form. The average leaking distance for the Thorndike minus the average leaking distance for the OptiView is going to be greater than what? Zero, right? Because it cancels out on the right side, correct? One number is greater than another number is the same thing as this difference between them is positive, right? And that's basically what my alternative says right now. Agree? So that's my null. Therefore, what's my alternative? H0, that mu for the Thorndike supplier minus the mu for the OptiView supplier is less than or equal to 0, right? It's going to be the opposite of my alternative. I keep writing the number 6. Somewhat stylized and ugly, but number 6. Okay, that's what I'm testing, right? Okay, good. Now let's proceed with the actual testing, ladies and gentlemen, right? So here is the bad news, okay? For JUMP to test independent samples, our data has to be stacked. Our columns has to be stacked, okay? What does that mean? And a lot of actually other pieces of software, JUMP is not the only statistical software, right? That's out there. That probably we should have discussed actually at the beginning of class. Now I realize that. Let me kind of step out of the two population bubble and let's discuss the software, okay? What are the popular software tools? And as you saw so far, and it's going to get only worse as the semester progresses, the statistical tests are very complicated, right? If you look at nuts and bolts of what's happening behind the scenes, it's just a lot of computations, formulas implemented in the programmatic code, right? So therefore, there are a lot of different software packages that can do pretty much the same analysis. So JUMP is the software from SAS. SAS at the same time has another piece of software that can do this analysis and then some. SAS is very popular in the world of data analytics, building the models, predictive models. Like how, for example, you predict, okay, hold on. How do you predict the customers or clients or employees who are going to leave, okay? How do you predict which flights are going to be delayed? Things like that, okay? So SAS is just another software. Then there is a product from IBM. IBM is one of the biggest software companies in the world, in the United States and in the world. And one product that they have is called SPSS. It stands for Statistical Package for Social Sciences, I believe, SPSS. And it's also using actually stacked data. Okay. Another popular package is, of course, Excel. Right. Excel is the sometimes it's called second best tool to do everything. Excel is so powerful; it can do a lot of different things. Right. But oftentimes, for any specific thing, there is a piece of software that does it better. Right. For example, you can plot the histogram in Excel. How do you do that in Jump? Literally 3 clicks, right? Or even 2 clicks, right? And you got yourself a histogram. In Excel, it's more involved. You have to specify your beans, so these intervals, right? So my lower bean starts at 0, and the next bean starts at 20, and then 40, etc., etc. And then it plots the histogram. So you have to do a little bit of, I wouldn't call it programming, but some stuff, okay, behind the scenes. So Excel is very popular. Then there is a program called Minitab. It's also popular. So these are the big ones. And pretty much most of the packages that can do population analysis, they require data to be stacked when you're talking about independently collected samples. And we have indeed independently collected samples, right? So how do we stack these things? Actually, I was kind of thinking about that yesterday. What I could give you is data that's stacked already, right? But then, of course, challenge would be how do we test normality, because it's kind of the mixture. It can be done still. But here's what I decided to do, okay? I'm going to give you, every time when I'll give you a problem about 2 populations, it's going to be column 1 and column 2, right? It's going to be your responsibility to read the problem and figure out if it's an independently collected samples or matched pairs. If it's matched pairs, that's analysis just the way it is, okay? You have to have them side by side because data points on the same line are matching, right? They have something in common, something that connects them. Okay? But if you, from reading the problem, if you figured out that data must be independent, then you have to stack them. And here's how you stack, okay? You go to the menu on the top. So we're going outside of our bubble, right? Everything that we did so far was in the distribution option, right? Now we're exploring something else. How to stack the data. You go to the tables, okay? And there is an option that says stack. So let's click stack. And first of all, I have to tell Jump which columns I want to stack. And stacking literally means I'm going to take one set of numbers and another set of numbers and place them in the same column, right? One pretty much on the top of another, right? That's what stacking is. I want to stack both of these columns into one, right? So I have to pick both of them and I'm going to say stack these columns. But what needs to happen is some of these numbers, half exactly actually, in my stacked column will come from the population Thorndike, right, from the sample Thorndike. Another half will come from the second sample, OptiView, right? So I need to keep an indication which number comes from what sample. So therefore, it's not just a stack of numbers. I'm going to have another column which will give me labels, right? This data came from sample Thorndike. This data came from sample OptiView. So therefore, I have to actually specify something right here, okay, where it says new column names. Stack data columns. How do you want to call it? So Jump offers us to call it data. Well, let's call it depth. How deep under the water it starts leaking, right? So depth. That's what actually we're measuring, right? And right under that, I have another one that says, what do you want to call your column with labels? So in other words, we should keep the reference, right? This data came from OptiView. This data came from Thorndike, etc. So label, what are the OptiView and Thorndike, what are they? Companies, right? Suppliers, companies, okay? Supplier. All right. And that's pretty much it. When I click OK, it will create actually, Patrick?
Where did you get that stack menu?
Stack menu, you go to tables and stack, okay? All right. And here it is, right?
So it alternates between the two companies.
Yeah, it alternates, exactly. You will see that. Yep, in just 1 second. So after I click OK, it will actually create a new worksheet for me, new data table. So it keeps my old data intact, doesn't mess with it. It creates a new data table for me. And you can see that here is my column that I named depth. These are the actual measurements, right, in numerical data, okay? And the second column is just my supplier label. And just like Phil said, you can see that pretty much how it creates the columns, I'm guessing, is it going line by line. So it takes sample 1, sample 2, sample 1, sample 2, next line. And it just basically alternates them line by line, right? So it does not take the first column in its entirety and then the second column. It doesn't really matter because, you know, the analysis is going to be done anyway, okay? It's just an observation. So,
So was it smart enough, I mean, I assume it was, to know, like if we had put suppliers first and then depth as opposed to typing depth before suppliers, would it have figured it out?
In the same column?
Yeah, I mean, would it have given them the right headers?
So let's see if I understand you correctly. So you're saying what each
When we were typing in the names, we typed depth first.
Uh-huh.
In the second box, we put suppliers. Could I have typed suppliers first and then depth?
Well, you have to kind of go by what it says tells you to do, right? So let's take a look. See, first one says stack your data. In other words, yeah, so they're not interchangeable, right? The first option here on the list is where your numerical data comes into. What we're looking for, exactly, the measurement. And the second one is just a label. Okay, company 1, company 2. Titles for your different columns. So you can swap them around. Okay? All right. So let's go ahead and test them. Okay? And testing of the hypothesis actually involves another type of analysis. So a couple of ways how I can access that. Well, here's the button, fit y by x. I can just click the button and it takes me to the window interface. Or alternatively, I can go to the analyze menu, analyze, fit y by x. Same thing. This is just a shortcut. So let's go analyze y by x. Okay? So let's kind of discuss that. Actually, yesterday when I was playing around with this tool, I realized that JUMP did it in a smart way, in a sense, because in a couple of days, we're going to discuss comparing 3 or more populations, okay? And comparing 3 or more populations for numerical data is done by a tool called ANOVA, Analysis of Variances, okay? In ANOVA, we have the notion of the measurement and the notion of the factor. What's a measurement? Measurement is something that we're measuring, okay? So this is a dependent variable, so to speak, okay? So here I'm measuring depth, how long does it take for the goggles to start leaking. That is my response variable, right? I'm analyzing numerical data, okay? I'm trying to distinguish if there is a difference between two different companies, right? Company OptiView and company Thorndike. So it's as if I'm studying, kind of broadly speaking, right? Does it matter which company do I pick as the supplier? That's the question that I'm addressing, right? I have two companies. Is that really important? Which supplier do I pick? Because if they're the same, that does make a difference, so therefore I can pick any supplier. But if I find that Thorndike is better or OptiView is better, that means that the supplier is actually important, right? So my factor of study, what I'm trying to investigate is the selection of the supplier having an effect on the quality of goggles, right? On the leaking depth, okay? So my factor of study is the company, and my measurement that I'm studying is how deep the goggles start to leak, okay? So this is the case for ANOVA, for analysis of variances, and this is how essentially JUMP analyzes two populations data, okay? So it sees the two populations data. It's kind of a limiting case, simple case of ANOVA. ANOVA is applicable for 3 or more populations. So here JUMP is saying, okay, well, how many populations at minimum we're comparing? 2. So let's do it in the same fashion as we do 3 or more. And that essentially is ANOVA, okay? So bottom line is, here I have to say, what's the response? What's the measurement that I'm trying to compare? And the measurement is what? Depth. right? And then what factor I'm trying to study? I'm trying to study supplier, right? Is the selection of supplier having an effect on the results, on the measurement or response depth, okay? So therefore, I have to actually place two different columns in two different places, right? And the easy way to memorize that maybe is response has to be always numerical, right? When you're doing ANOVA analysis or when you're doing t-test, just like we're about to do, your response or your measurement that you're trying to analyze has to be numerical. So if you have a choice here, right, one column is numerical with the blue triangle and another column is categorical with this red icon, and blue triangle goes first and the red triangle goes next, okay? So that's the easiest way to see that. Okay, so let's click OK. And all it does basically right now is it plots for me, you can see, feet y by x. That means that you have something going on horizontally, x, and you have something that goes on vertical, right? Two different variables. All right. So it just plots a bunch of points, right? So for the OptiView, you could see that the leaking depths were all over the place, right? OptiView started to leak as early as 68 meters, and the toughest pair of goggles was holding up until 119 meters, right? What happened with Thorndike? Thorndike, the weakest goggles started to let the water at 60 meters, and the toughest pair of goggles was holding up until 128. So this is just a scatter plot, right? Two different levels of the variable horizontally, and vertically I have all of my measurements, right? Let's take a look at the specific measures, right? What we're trying to analyze is actually the mean, right? That's the idea. We're looking at the means. So let's go to the red triangle menu because there is nothing else to click, right? And from this menu, let's go ahead and pick up mean and standard deviation. That will give us some statistical summary of what's going on, okay? So what do we see? We were suspecting that the mean for the, at least we're testing for that, right? That mean for the Thorndike goggles was higher than the mean for the OptiView goggles, right? Remember, we discussed that in the previous class. When you're testing hypotheses, it's a good idea to look at the point estimates before you do the testing, right? Because if you suspect a fire, there should be an indication of a fire in form of a smoke. So, in our case, smoke comes in the form of X bar, right? We're suspecting that the mean for the Thorndike is higher, so therefore I should see pretty much the same thing in terms of X bars, right? Do I? Mean for the Thorndike, mean distance where it started to let in the water, right, was 93.7, correct? And for the OptiView it was 88.8. So therefore, here, let's go back to the notes. I'm going to say mean for the Thorndike was 93 point, what was that, 7? Yes. 93.7, and the mean for the sample OptiView goggles was 88.88. So, based on my point estimates, does it look like I have an evidence, maybe strong, maybe weak, I don't know yet, that supports my alternative hypothesis? Looks that way, right? Because based on just this small sample, Thorndike, that is a Thorndike, right, is looking better, right? Their leaking distance is actually higher, the average, of course, than the leaking distance for the OptiView. So therefore, I have at least some indication that my alternative can be supported, right? And then, of course, what do I have to do after that? How do I pick between null and alternative? I need to find out the p-value, right? So how do we find the p-value? Let's go back. Okay, well, you probably guessed. For the p-value, I have to go to the red triangle menu, right? And there are two options, actually. Obvious one is t-test right there, right? But we're going to use, actually, let's take a look at both of them, okay? But first, we're going to see this second option, which is not so obvious, right? And when you hover your mouse over this option, there is a helping, it's called tooltip, right? Helping message, which says, this option contains t-test, ANOVA, which we didn't study yet, but we'll talk about that in a couple of classes, right? And the report for the means. And this one is a t-test just another t-test. So what the hell is the difference, right? This is a t-test and this is a t-test. Which one do we use? Let's use both of them. Let's look at the first one first. Yeah, let's look at the first one. When you click that one, it gives you the whole bunch of different output, right? Okay, so let's look at the t-test, because that's specifically what we're looking for, right? Because we kind of actually, like, how do you formally approach this problem? You get something like this, right, on the homework or the exam, or in the real life, in the future, right? You start right here, compare two populations, right? And you say, data type, obviously interval, right? And you say, what am I doing? I'm comparing averages, or at least that's the plan. So therefore, I'm dealing with central location. After that, independent samples and matched pairs. And then you're saying, goggles, 50 from manufacturer 1, 50 from manufacturer 2, have nothing to do with each other, completely random samples, or probably independent. And then it says, well, are your distribution normal or not? You're saying, let's test them. Test sample 1, sample 2, you say, both normal, what do I do? T-test. But there are two flavors of t-tests, okay? So let's take a look at flavor number 1 that we have right here. Okay? Let's look at the output. First of all, here's what it says. Difference is 4.82. Where do you think that comes from? And what is it? What's the difference? 4.82.
That's the difference between the means.
That's the difference between the means, exactly right. So basically, it says that if you take the mean for the higher OptiView and subtract mean for the lower, that is going to be your 4.82. Okay, that's your point estimate for the difference of mu1 minus mu2, right? Because it's all based on samples, right? We're not talking population here, we're talking samples. So this is my point estimate of the population difference. Okay, that one. All right, so now that we have that cleared out, essentially we're comparing that against 0, right? Well, because here's my hypothesis, right? I'm comparing that against 0. So essentially the test is going to try and determine, is that number 4.82 far enough from 0 for us to claim that there is actually a statistical difference between Thorndike and OptiView, right? What if the distance would be not 4.82 but something like 0.53? What would you say? Is that a big difference between them or not so big? Not so big. Probably it's kind of because of variability, right? Sample number 1 is highly variable, sample number 2 is highly variable, right? So purely because, you got lucky sample from Thorndike and not so lucky sample from OptiView, that's how this difference showed up, right? It's possible, okay? But once your difference starts to get bigger and bigger and bigger, then you're going to say, whoa, wait a minute. It looks like these distributions are really far apart from each other, right? And therefore, one is definitely better or statistically worse than another, right? So, therefore, this distance, 4.82, this distance we need to test. Is that really that different from 0, given that both samples have distribution? They have the width, right? Not all the numbers are the same. If all numbers would be the same, that would be a clear-cut case. But they're not. There is a distribution. Okay? So, are we looking in the right tail of the distribution or the left tail of the distribution? Here is what we're testing. Tell me. Right tail of the distribution, right? How do we know? That's my alternative, right? Alternative says we're looking at numbers greater than 0, right? So therefore, I'm greater than testing greater than hypothesis, so I'm looking at the right tail of the distribution. And here is the distribution of all possible differences, right? It kind of revolves around 0. So this is what remember, when we test hypothesis, we start with believing the null, right? And what does the null say? Null says that the difference between mu Thorndike and mu OptiView is 0, right? 0 or less. So there is no difference between them, right? Difference between the averages is equal to 0, right? That's our null hypothesis. What we saw is the sample 1 and sample 2 that gives us the difference of 4.82, and that number right there, okay? And because we're testing the right tail of the distribution, because my alternative is greater than, my p-value is right here in the left tail. Okay? So therefore, for the I have three choices, right? That's for equal, not equal, alternative hypothesis. That one is for greater than, and that one is for less than. I have hypothesis greater than 0 alternative, right? So therefore, that is the one that I need to use, 0.0372. Now, here is basically what this test is using, the assumption, okay? You see on the top it says, assuming equal variances. So this test, and that's also underlying assumption for ANOVA. Again, we didn't talk about ANOVA yet, but kind of advertising it, right? In the future, we'll take a look at ANOVA. ANOVA, when you're measuring, when you're testing ANOVA, it assumes that your samples have equal variances, or equal standard deviation, which is the same, right? So same here. It assumes equal variances. Well, the easy way to see if variances are equal or not is to look at the standard deviation, really, right? Variance is very closely linked with the standard deviation. So let's take a look at, do we have still numerical summary somewhere here? Yeah, means and standard deviations. You see that? For OptiView, standard deviation was 11.73, right? For Thorndike, the standard deviation was 14.82. Do they look kind of close to each other? They do, right? There is not much difference among them. If one was 11 and another 22, then you will say, whoa, that is twice the variance, right? Twice the variability. But in this case, they're fairly close. So therefore, it's kind of a justified assumption that variances are the same. Okay? So that t-test is done assuming the equal variances for sample 1 and for sample 2. So here's my p-value, 0.0372. Let me go back right here. So for this hypothesis, p-value equal 0.0372. What significance level do I use? 0.05. Okay, so alpha, let me erase some of that stuff. Alpha is 0.05. So what happens after that?
P is low.
Yep.
Null's gotta go.
Yep, p value is low, lower than alpha, right? Which means we reject the null, as we always do, in favor of alternative. And what does my alternative say? Alternative actually is still...
There's a difference.
Yeah, there is a difference. Moreover, Thorndike is statistically better, okay, than the OptiView. Make sense? So therefore, what's the executive decision? Because at the end of the day, we have, imagine yourself to be part of the Olympic committee, right? We do this test, and test says statistically Thorndike is better. So now, what do we decide? Yeah, we're going to use a new supplier, right? Because apparently their average leaking distance is better than the previous one. Okay, that's the decision that the American Olympic Committee would do, not the Russian Olympic Committee. Russian Olympic Committee does things a little bit differently. Just at that. All right. Now let's take a look at actually another option, right? So this one we picked again from the red menu, right? We said means, ANOVA, and pooled t-test. Okay. Let's take a look at this t-test. Let's see what is exactly the difference, right? Why are we using this test and not the other test? What's the difference between them? So let's ask for this one, t-test, and apparently it shows up at the bottom. It just uses a different formula. The difference is that our first test that we used assumed equal variances, right? That sigma 1 is equal to sigma 2. This test that we just used recently, just the latest one, right, assumes unequal variances. So basically it's saying that sigma 1 is different from sigma 2. And therefore, behind the scenes, it uses slightly different formula, okay, in order to calculate the t-value and therefore calculate the p-value. So you can expect p-values to be slightly different. Let's see, are they really all that different? They're very close, right? The one that we used, 0.0372, and this one is 0.0373, right?
So why is it red, highlighted red?
Why is it highlighted red? It probably understands that since your difference is positive, and you're comparing against 0, you're looking in the right tail. Yeah, you're looking in the right tail. So it kind of pushes you towards the right thing to test, right? Visually, it says, hey, that's probably what you mean to test, okay? That's what would be our choice. All right, make sense? Patrick.
Should we Should we always use the equal variances one, unless it says they have equal variances?
Yeah. Should we always use equal variances? I guess that's going to be a judgment point for us. Yeah. So before you decide which way to go, whether or not to use the equal variance test or unequal variance test, a good rule of thumb would be to take a look at means and standard deviations and evaluate for yourself, right? Look at standard deviations. In our case, it was 11.7 versus 14.8. You will say, well, they're fairly close. So I'd say they're equal. Let's go with equal variances. If you see huge disparity, well, not huge, large disparity, right? One of them is 30, another is 45. It's 50% larger, right? And you're saying, whoa, clearly this standard deviation is higher. So therefore, let's go with unequal variances.
What about, like, where's that fine line, you know?
Fine line?
50% or so?
Again, this is a judgment call.
Okay.
This statistics is science only partially. Another part of that is science. Where do you draw the line in the sand, right? Where do you start seeing big differences as opposed to pretty much the same?
Subjective.
Judgment call. Yeah, largely it's a judgment call. Well, I got to tell you that there is a test, actually. There is a rigorous test that tells you if the variances are the same or are they different, statistically. But I don't want to get into this. It opens up another whole can of worms, right? So now, before we test the hypothesis, we need to test the variances, see if they're same or not, and then pick equal variances test, t-test, or not equal variances, t-test, right? So that would be like digging deeper, right? But yeah, let's just use healthy dose of judgment. Let me put it that way. Just look at the standard deviations and decide for yourself, right? Are they look close? Are they looking close, or are they looking far apart from each other, right? Make sense? Okay, the last thing that I wanted to illustrate today, we still have a little bit of time, right, is why are we even doing this test, okay? T-test. So where is that coming from? So here is basically, like over the years of teaching this course, here is the illustration that I came up with, okay? I'm comparing in this problem, right, let's be specific. Let me actually, go ahead and draw the horizontal line. So in this problem, Thorndike turned out to be better, statistically better than OptiView, right? But here are a couple of possibilities how it can happen. Suppose that Thorndike is in fact better, okay? So therefore their average leaking distance for the Thorndike is actually higher than the average leaking distance for the OptiView, okay? Mu OptiView. All right? One case, what can be happening is, and you saw that in JUMP actually. If you look at the distribution of points, points are not all the same, right? They're all scattered. So that means that there is a variability in the goggles, right? One pair of goggles is different from another pair of goggles. So therefore, they're all over the place. Some start leaking earlier, some start leaking later, but they're all different. Okay, but suppose that somehow these two companies have a pretty solid manufacturing process. That means that while there is still variability, it's not very big. So in this case, I'm going to have this, okay? This distribution is going to look like that, fairly narrow, and this distribution is going to be fairly narrow, okay? OptiView, suppose, uses very similar process, and they have also distribution, okay? Like that. But you see what happens? There is an overlap, right? Between the two distributions in this area, okay? So what can happen? Whoopsie. So therefore, what can happen is, most of the time, in this case, I take the sample from Thorndike, okay, sample of 50 goggles from Thorndike, it's somewhere here, for example, okay, or somewhere over here. I take a sample from OptiView, and it ends up somewhere here, or somewhere over here. In this case, the measurement will show most of the time that Thorndike is better, right, because it's higher, right? There is a distance. But every once in a while, I will have unlucky samples, right? Every once in a while, I'll have sample from the Thorndike, which is uncharacteristically on the low side, somewhere over here, right? unlucky sample. Very rare because it's in the tail of the distribution, right? And uncharacteristically high sample from the OptiView, which is on the high side, right? And therefore, I will have a reverse relationship. Thorndike, on average, will actually show worse performance, right, than the OptiView. So this is what will happen if I have fairly well-defined distributions, just like that, right? They do overlap, but the overlap region is fairly small, right? In this case, probably most of the time, Thorndike is going to be better, right? But here is another possibility. What if their manufacturing process, and by the way, before we proceed there, and if I have these two distributions which are fairly narrow, right, then probably my test will demonstrate difference in terms of averages, right? It will tell me that, hey, I tested the population differences, and the test takes into consideration sigma 1 and sigma 2, both of them, okay? So it actually looks at how wide are both of your distributions, okay? So the test will tell me, given the width of two distributions, high likelihood that Thorndike is actually better than OptiView, okay? But here is another possibility. What if I have wider distributions, okay? Same averages, but distributions are wider. So here is my mu Thorndike, same, mu for the new supplier, candidate, and here is my old supplier, OptiView, okay? Same thing, but now distributions are much, much wider, right? This one is like that, and another is like that. That is a possibility, right? Then you can see the overlap is actually much bigger, right, between the two distributions, correct? Overlap is much bigger. So therefore, very frequently, you will have a case when Thorndike is low and OptiView is high, right? Sometimes you will have case when Thorndike is high and OptiView is low. So because the variability is so high for both samples, right, for both distributions. And therefore, the test will, obviously your sigma 1 is going to be much bigger and sigma 2 is going to be much bigger, right? So the test will take both variabilities, both sigmas into the consideration, and in this second case, this is our first case, this is our second case. So in the first case, the test will likely show you that, yes, Thorndike is bigger than OptiView, because variability was small, and therefore you can see clear separation of distributions. But if there is a big overlap, then test will actually show you the big p-value, and therefore you will stick with the null, which will tell you that probably they're not that different. And the reason, and you can see that, right? They're not that different because distributions, they look very similar. It's like one is slightly shifted compared to another, right? But overall, there is a great deal of overlap between them, okay? So in this second case, the test will likely give you a high p-value. So here you'll likely see low p-value and rejection of the null hypothesis. And here you will likely see high p-value, okay? And therefore you will keep the null hypothesis, right? But the difference really between these cases is variability. One case is more variable than another, and therefore the picture is much more obscure, okay? That's why it will probably not find much difference in the second case. So it's not just the difference between the means. That's what we're testing. But another part of the puzzle is how wide is your distribution. If they're too wide, overlap obscures the picture, okay? So that's kind of an informal way to see why exactly do we test for, how does the variance or standard deviation plays into this whole hypothesis testing, okay? Make sense? All right, so there are two problems for tomorrow in terms of the homework, one for chi-square, another for testing of the populations, 1 versus 2, okay? And tomorrow we'll start by going over the homework, and after that I'll give you an exam, and then we'll continue talking about two population comparison, okay? All right, see you tomorrow.